Thanks for the kind introduction, and I would like to thank the organizers for the wonderful conference. Today, I would like to talk about some recent results on the mixed local and non-local problems. So this is a joint work with Mengyao Ding, is associate professor in HIT, and Yuzhou Fang is an assistant professor, and Dingding Li is my second-year PhD student. So my talk will include 3 parts. First, I will give a quick review for the non-local or fractional Laplace equations about the regularity theory, and then move to the non-local problems with non-standard growth. And finally, I will state our main result. Maybe due to the time reason, I will skip the concrete proof. So let's start from the standard fractional Laplace equation. So we all know that the first result is due to, for the standard fractional Laplace equation, negative Laplace s u equals 0. So this operator defined by the Cauchy principle sense. So the first result is due to Caffarelli and Sylvester in 2007. They proved a standard Harnack. The assumption is U is non-negative in the whole space Rn. And then Kasman gave a counterexample such that for the solutions of the standard negative Laplace s u equals 0, and if we just assume that U is non-negative in a small ball, is locally non-negative, then the standard Harnack is failed. So we know that we should add some tail term. So this is the Harnack. And next, about the Holder continuity, and we can find the result by Sylvester and Kasman, 2 different papers. And the boundary case, the boundary Holder continuity is from Ross, Alton, and Sarah. So this is different from standard Laplace equation. And for the inhomogeneous case, so the interior SP estimate, we can find this result from Hongjie Dong and Kim's GFS paper. And Cauchy proved estimates in Sobolev and Nokotsky space, Sobolev type regularity. And for the system case, very recently, and DeFilippis and Minzhang Novak, so consider the first partial regularity for the systems case. So there are many results. I just mentioned a few. Next, let's move to the quadrilinear case for the fractional P-Laplacian equations. So here is the definition for the operators. So the kernel K, something like that, is AXY, the coefficient, times the kernel, the standard kernel, X minus Y, the absolute value, to the power negative N minus SP. So the standard definition. So if the coefficient A is just a positive constant, then we have the standard fractional P-Laplace equation. And the solubility in the viscosity sense of the associated derivation problem and the connection to the standard P-Laplace equation can be found in ESI and Nakamura's paper. So this is the very first paper for the fractional P-Laplace equation. And then the local boundedness and the Holder continuity and the Harnack can be found in the De Castro, Cauchy, and Palatucci's a series of papers. And compared to the standard fractional Laplace equation, for the P-Laplace case, in the viscosity sense, the Holder continuity is from Lindgen's paper. And then the global case is due to Anazotto, Mosconi, and Skosina. And then the local boundedness and Holder continuity and Harnack equality is from, for the more general, non-differentiable functionals, for the many methods, such kind of functionals is from Cauchy's paper. And very recently, there's a new paper from Dinin, Novak for the cardinal-Zygmunt estimates. Okay, next I will give some special cases for the fractional P-Laplace equation. The first one I would like to say, for the inhomogeneous case, there was a right-hand side f. So if for the degenerate case, if p bigger than or equal than 2, s belong to 0 to 1, and f, the right-hand side belong to WSP prime space, then the solution U enjoys higher differentiability. So it means that if s less than p minus 1 over p, it means that if s is small, then you belong to W top p. So here t is any number between 0 and s. So if s is bigger, then the gradient of u belong to W top p. Tau is like this range. So this is for the degenerate case. And then if p is still bigger than 2 and f belong to I of gamma, gamma is a number depending on, for example, gamma bigger than n over sp. And then Brasco-Lingen and Spicora obtained the sharp Holder index for the weak solutions. So it means that the Holder index alpha belong to 0 to capital theta, this range. And for the singular case, we can find the result from Garin, Lingen, and see also Dinin, Kim, Lin, Novak's paper, MA's paper for the recent contributions. So this is the first special case. And the second special case, just consider very the homogeneous case, right-hand side just 0. So there are two very interesting papers from Berglin, Duzer, Liao, and collaborators. The first result is p bigger than or equal than 2. Then s belong to 0 to p minus 2 over p. So improve the index of the Brasco-Lingen's paper to a new range. So u belong to W gamma q for any q belong to p to infinity, and gamma belong to s to sp over p minus 2. If s bigger than this number, then the gradient u enjoys the Sobolev regularity W alpha q for any alpha belong to this range. So I think this is a very nice result. And from the singular case, we can also find another paper. And for this one, this is the second special case. Next, let's move to the gradient level for the fractional Laplace equation. So if we consider such kind of equation is fine, is old, and satisfies this growth condition, the special case is phi t equals t. And this equation, and Dinin, Kim, Li, Novak prove that if right-hand side is 0, then any weak solutions belong to C1 alpha locally. So if there was right-hand side, if mu is a standard random measure, and s bigger than 1/2, then the solutions have the gradient bound, is a non-potential theory. And see also the Kusi Novak series paper. It is another special case. So indeed, there are many results on the fractional P-Laplace equation. For example, other results for the eigenvalue problems, and Kusi-Minjani theory, and about the potential theory and self-improving properties, and about the obstacle problems and equivalence of different solutions, and Wenxiong Chen, Congming Li, and consider the symmetrical solutions by the moving plane method, and the parabolic case, and many other results. It's a huge literature. I just mentioned a few of them. So next to the second part of the non-standard growth. The first one, the model is the variable exponents fractional Laplace equation. So here P is a function of xy, And S is also a function of XY. So the local boundness holder continuity can be found in Oak and Chucker-Kim's paper. So it's a variable exponent case. And there another special case is non-local PQ growth. So it's compared to the corresponding to the standard local case, is PQ growth. So for this kind of equation, f equals 0 or is not 0, there are some papers from Go, Kummer, Srinada, and Giacomi, Kummer, and Srinada, several papers. And a special case is called non-local EP 1P growth. These models can be found in a very recent paper, Goni, Mazin, and Tornado. So this is considered a parabolic model, 1P growth. Okay. So, and for more generous growth case, if G is satisfied some growth, something like that origin space, origin growth. So there are also some result about the holder regularity. Harnack estimates from Bien, Kim Oak's paper, and Fang and myself, and Chucker Kim Widner paper. And for the potential estimate and the Wiener criterion can be found in Kim Lee's paper. And we also consider the Heisenberg group sighting. Okay, next we move to called non-local double phase problems. If this is P growth, fractional P growth plus a coefficient, and here is a Q growth. So this kind of equation was first introduced by De Philippis and Pelletucci. And they, in their GD's papers, they considered the local holder continuity for the bounded viscosity solutions under the assumption that S bigger than equal than T and satisfies some other conditions. And the self-improving property and that can be found in Scott Mangacha's paper. And we also considered the non-local double phase problems considered in the weak sense. Distribution sense prove the local holder continuity and considered the inner relationship for the weak and viscosity solutions. And on the contrary, for the case T is bigger than S, and Bien Oak Song consider the holder continuity and the conditions TQ less than SP plus alpha. Alpha is the holder component, holder index for the coefficient A of XY. Okay, so this is a non-local double phase problem. So indeed, the original one is from the local double phase problems. This kind of function or functional was introduced by Zhukov in the context of homogenization. And the basic regularity theory was developed in a series of papers from Colombo-Minjani and the collaborators. And there are many very good results for such kind of double phase problems. So just to mention a few of them. For example, the local boundness on the holder continuity and was proved by some sharp assumptions and exponent PQ. And here is the boundness. And if we assume that U is bounded, many measure of weak solutions are bounded, the coefficient is holder, and Q less and equal than P plus alpha, then the solutions U belong to C1 beta locally. This is Colombo-Minjani's AMA paper. And the very more general models, the PQ, non-uniformly shorter theory can be found in Philippis-Minjani, two papers. And just to mention, as the former speakers consider the nearly linear growth case. And there are some results for the parabolic case. It's due to Kim, Ganunen, and Maureen. Two papers here, I just mentioned Ahmad's paper, and another paper is NODA. And for the ellipse truncation papers for the from the GFA's paper. And for the other results, for example, removability of singularities from Chalabica and the Philippines, and the properties of a superharmonic functions, Chalabica and Zotowska and Golosyan papers. Now here, just I mentioned another special case where 1p growth, that's mentioned by the Bach and Giga in several papers consider this kind of problems. There are many other results. I just mentioned a few of them, including Macellini, Belzi, and Bienrad-Lazgu, Tachikawa, and so on. And there's a special case, the last slide consider double phase problem is PQ growth. Here we just mentioned a very special case from De Philippis and Mingioni. They consider mixed local and non-local problems. So the local term is P growth, and the non-local terms is Q growth. So they prove that if U is a matter, and the local term is a mean term, it means that if P bigger than SQ, so this power SQ can be seen from the scaling, this power, and its boundary is smooth, and F belongs to LD, D satisfies some condition. Then the gradient U is locally holder continuity. So this is for the mixed problems for the non-standard growth. Okay, next I will state some result of my result. The first one is for the mixed local and non-local problems. So De Philippis and Mingioni's paper concerns with the local term is the main term. What will happen if the exponents located in the other case, the SQ, bigger than or equal than P? So it means that the non-local term is the main term. What can we say for the regularity? So our result is like that. Indeed, we can consider more general case is growth, local growth, Fx gradient U, the non-local part. Here we add a coefficient, so inspired by the double phase. So we add a coefficient AXY. If AXY satisfies the symmetry condition, and AXY there is non-negative. So here is A0 is the lower bound, and capital A0 is the upper bound. So we can obtain the following three results. The first one is the boundedness for the many matters. So the mean two is Degenerate type iteration. The second one, we can obtain the holder continuity for the many matters. So the mean two is the expansion of positivity. So this method is due to Di Benedetto, Giannazza, and Vesperi. And the third one is Harnack. So in order to obtain Harnack, we need first prove weak Harnack, and plus the supernormal estimate for the many matters, and plus tail estimate. So we give the result quickly. So first is boundedness. If the coefficient AXY, if there's a positive lower bound, A0 is bigger than 0, strictly bigger than 0, and then if F belongs to L gamma, gamma satisfies some assumption, then any many matters have the following the bounded estimate. The supernorm of U over the B R over 2 can be controlled by, this one is the integral of U plus, and the second term is the tail term. The third term is the inhomogeneous term. This boundedness result. If the coefficient can be 0 at some point, it means that AXY is non-negative. Then we can also obtain the boundedness result, but we need add some conditions on Q over P. This condition, we can obtain the boundedness result, but we don't know what is the upper bound. Just know it's bounded. And for the holder continuity and Harnack, we need to assume that AXY, there is a positive lower bound. Otherwise, we don't know how to do. So A0 is bigger than 0 strictly. that we know the mathers is C alpha locally, and satisfies the Harnack. So it's tail term and the inhomogeneous term. So this is our first result. Second result, we consider the higher Sobolev regularity for the mixed problems. The last problem is one term is local term, another term is a non-local term, but the power is different. If the power is the same, here is P, the second term is also the power is P, then we want to prove that the higher Sobolev regularity. So here this is the definition for the tail, and MR is defined by the L infinity norm of U plus tail term. And our main tools is the finite difference quotient technique and the energy method and tail estimate. Our result is the following. The first result is if U belongs to W1P and LSP P-1 belongs to this space, is a weak solution of the mixed problem. If P big and equal than 2, if U is bounded, then the combination of gradient of U. So this quantity belongs to W12 locally. So this is the estimate. And if P bigger than 1, less than or equal than 2, if U is locally Lie-piece continuous, then we know that U belongs to W22 locally with this kind of estimate. So this result recovers the standard P-Laplace type equations. It is same to the P-Laplace equation. And if the next result is W1Q regularity for Q bigger than P. So from the definition of weak solution, we know U belongs to W1P. Then we can further improve the regularity from W1P to W1Q if P belongs to 1 to 2, the singular case. For the degenerate case, if P bigger equal than 2, the W1Q regularity was proved by Gary and Lingen in 2023. And the next, there is some higher order Sobolev regularity. So if P bigger than 2, U is locally bounded and satisfies U belongs to W1Q, then the gradient of U belongs to W alpha Q. So for any alpha belongs to 0 to 2 over Q, this range. And if P bigger than 1, less than or equal than 2, if we further assume that U is locally Lie-piece continuous, then we also can obtain that the gradient of U belongs to W beta Q. So for any Q bigger than 2 and beta belong to the same range to the degenerate case. So we unified this result. Indeed, there is a very special case called nonlocal EP growth, nonlocal 1P growth. So here's the growth, say the power is 1. Here's 1, here's P. So here we can almost obtain that called almost the Lie-piece continuity for large SP. So here we just consider the case for P bigger and equal than 2. So if SP is big, then U belong to C0 gamma 1 for any gamma 1 belong to 0 to 1. If SP is small, then U belong to C0 gamma 2 less this range. So from the Butcher, DiPiro, and the collaborator papers, we know that if we just consider if there was the first term, is called S minimal functions, we know that the mathematics is continuous. But here we add another term, is a regularized term. So add P growth, then we can improve the regularity from continuous to C alpha. Almost Lie-piece continuity can be obtained. Finally, I mentioned the last result for the non-local double phase problem. So just as mentioned before, in the viscosity and weak sense, we have proved the local Holder continuity for the solutions, but we don't know how to. There's no result about the Harnack equality for the non-local double phase problems. So inspired by the result of Cozy, GFA papers, and Liao's paper. So we proved the following result about the weak Harnack. So give some definitions for the many methods. So defines HR is the P minus 1 plus Q minus 1 growth. So this is defined by HR. And capital HR is P growth. And a tail is this is the tail definition. Here is the many methods definition. Here is the standard in some sense. So our result is there are three kinds of weak Harnack. The first weak Harnack is the standard. So we need to assume that AXY is Holder continuity with respect to the two variables. And this condition is some distant condition, alpha less than TQ less than equal than SP plus alpha. So then we can prove the standard weak Harnack. So the infimum of U bigger than this average of integral, and the tail term, because it's a non-local double phase, there are two tail will appear. So here, the exponent epsilon less than 0 to 1 is standard Harnack, weak Harnack. So this kind of weak Harnack for the local case can be found in the Baroni, Colombo, Mindoni's paper. So they have proved the weak Harnack. Indeed, they proved Harnack for the local case. And another condition, alpha less than TQ, is used to guarantee this is integral converges. So in this condition, you ensure that. Because here the two terms are the non-local case, so it inherits both difficulties from the double phase problem and from the fractional operators. So when we impose the condition A is holder, so we can rewrite the equation. So his P grows. So here is 1 plus. So this quantity can be controlled. Then all is fine. So we need, if we assume that A is something like that, x minus y absolute to the alpha, then this quantity is almost a constant. So we can see that, something like that. Okay, and that's 1 minute. So the second weak Harnack is this one. If U is a matter and a bounded matter, then the weak Harnack we can improve the integral power from epsilon to P minus 1 or Q minus 1. So I have mentioned that this result is more motivated by the Liao's paper. And the last one. So if we assume that A has a positive lower bound, then we can get another weak Harnack. So this weak Harnack is more reasonable because in the local case it's U minus and U plus. U minus is on the left hand side, and U plus on the right hand side. So this is the third weak Harnack. But we don't know. Finally, I want to say we don't know how to prove Harnack if the coefficient is not a positive constant. We don't know how to prove. Okay, this is my talk. Thank you.
Other comments or questions? Yes, please.
Thanks for a nice talk. I just wanted to ask if you are aware of the results about Laurentiev phenomenon for this non-local double phase. So there are bounds which one could be interesting to see if your results coincide with the one I have for the example, just to see how sharp are the bounds for the P, Q, S, and T. But maybe I can send you your paper because you don't cite it, so maybe you just don't know about it. Yes.
I don't know if it is sharp. I don't know.
Okay.
Sorry, I don't know.
And what about so for the non-local double phase, you have only this weak version of Harnack, right?
Yes.
Can you tell what is the difficulty?
The difficulty, as far as we know, the difficulty is like that because here's the weak Harnack, the infimum of U bigger than this quantity. And for the estimate of supremum of U, the upper bound and the lower bound cannot match. So I tried several times. The condition imposed on the coefficient is A is a positive constant. Otherwise, I don't know. Maybe Professor Minjani can give some comments.
Thank you.
Thank you very much.
Are there questions or comments?
You did a very good job of things that this double phase model was a toy model because it is still uniformly elliptic. You know, if you go back. There is this go back. Stop. Next. So when you say more general model, actually these papers with Christiana, these are the real non-uniformly elliptic problems because the double phase is locally still uniformly elliptic. So it's a, let's say, a toy model that we did at that time to start to understand how to do Schauder estimates for something which was anisotropic, but it's still pointwise uniformly elliptic. So the real the real beef is in this later papers with Christiana. That's because this is non-uniformly elliptic, purely non-uniformly elliptic. That's the only comment.
Okay, thank you for your comments.
Other comments? Okay, then if not, we thank the speaker again.